Hello, AP Chemistry students. I hope you guys are doing well with your distance learning and that everybody is staying healthy. All right, so one topic we didn't get around to covering yet with classes being changed the way that they have is solubility equilibrium. So we'll go through some examples of that today. So you might remember back earlier in chemistry, you learned about solubility rules. That when some ions are put together, positive and negative ions, they give you something soluble, something aqueous. When other positive and negative ions are put together, you end up with something we said was insoluble or a solid. In this example here, potassium chromate added to aqueous silver nitrate forms a solid silver chromate. Well, more of the truth to this is that even though it does for the most part form a solid, some of the ions still are in solution. So we'll be taking a look at that equilibrium here. So we've already looked at other equilibrium constants, Kp, Kc, Ka for acid equilibrium, Kb for base and water equilibrium, Kw. Here we're going to look at something called Ksp, solubility equilibrium or solubility product. So it's kind of the study of what actually dissolves or what actually breaks up into ions of these things that we call insoluble ionic compounds. That does again sound kind of weird because we're talking about something that is mostly a solid, but everything does, even these insoluble ionic compounds, do form slight amounts of ions in solution before they reach equilibrium. So, again, Ksp, solubility product equilibrium constant, has one particular value for a given solid at a given temperature. The solubility is kind of your equilibrium position. So here's an example of one of these equilibria that we're looking at. We've got BiS3 solid in equilibrium with 2 Bi3 pluses and 3 S2 minuses. Those are the ions that it forms. S2 minus, because it's in the second column away from the noble gases, it forms 2 minus. And then you have, just to balance out the charge, 2 Bi3 pluses there. The Ksp expression then for this, just like any other equilibrium constant, would be products over reactants, but our reactant is a solid, so that's not going to be included in the expression. So our Ksp expression is simply the concentration of Bi3 plus when this reaches equilibrium squared times the concentration of the S2 minus cubed. You can find tables of KSPs in like the back of the book, in the chapter, or on the internet. This is an example. You can see that for the most part, well, these are all values that are less than 1, but for the most part, they're very, very small values for the equilibrium constant expressions. So, just going through another example of writing an equilibrium expression for this. CaF2 solid in equilibrium gives a small amount of Ca2 plus and F minus, 2F minus. And so if we are going to write the expression for this, products over reactants, but again the reactant itself is a solid, so that won't be there. So if we're just going to fill this in, we have Ca2 plus and F minus squared. Again, we're only looking at the aqueous solutions because we don't include solids in equilibrium constant expressions. So once again, we had Ca2 plus and F minus squared. All right. Why don't you pause the video here and see if you can give this one a quick try. First, write out the expression for this, what it would break into, and then see if you can write the KSP expression. Give it a try, and then come back and unpause the video. Okay, so hopefully you gave this a try on your own already. So we're taking this solid, and this would break into 3 magnesium ions, 2 phosphate ions, and based on the fact that we know that phosphate is 3 minus, and based on its position in the periodic table, we should also know that that would be Mg2 plus. So 3 Mg2 plus and 2 phosphate ions. So when we're writing out our KSP, we'll have Mg2 plus cubed times PO4 3 minus squared. And that is our KSP expression for magnesium phosphate. Just for good measure, let's try one more. Go ahead, pause it, write out your equilibrium expression here, and then write out your KSP. Give it a try, and then come back and unpause it to double check. Pretty straightforward for this equation. BaSO4 solid breaks down into a small amount of Ba2 plus ion and SO4 2 minus ion. So writing our KSP here, we simply have the concentration of Ba2 plus at equilibrium times the concentration of SO4 2 minus at equilibrium. They're 1 to 1. So our exponents on each of those ions is also 1. So you might be noticing here that if nothing else, this is a good review for what ions form particular ionic compounds that you learned way early on in chemistry, and that topic kind of resurfaces in KSPs. All right. Well, the magnitude of the value of the KSPs can sometimes be used to compare the solubility of two solids, especially if they have similar chemical formulas. So, for example, if you look at silver chloride, silver bromide, and silver iodide, which of those would have the highest molar solubility in water? Well, they all have very similar formulas. You've got AgCl, you've got AgBr, and you've got AgI. And in their equilibrium, they're going to form very similar things, Ag plus, Cl minus, Ag plus, Br minus, Ag plus, I minus. Or more importantly is that they all form 1-to-1, one positive ion, one negative ion. So they're going to be very comparable to one another as far as how they dissolve. So then you can just look at the KSP values. Which one is the highest Kp value? That one is going to have the highest molar solubility in water. So highest KSP, highest molar solubility. That's pretty much all there is. So how about if we compare these? Barium sulfate and calcium sulfate. Again, very similar formulas. You've got BaSO4 versus CaSO4, and they form similar things, Ca2 plus SO4 2 minus, or Ca2 plus and SO4 2 minus, 1-to-1. So you can compare those straight to each other. Which one has the higher KSP? Calcium sulfate has the higher KSP. So it is also going to have the higher molar solubility in water. Nope, I missed one. Lead 2 sulfate. Calcium sulfate is still the highest, so we'll still stick with that answer. So if you're comparing several salts of a given temperature, does a higher KSP value always mean a higher solubility? Well, the answer to this is no, because if they don't form very similar numbers of ions, then you can't necessarily just directly compare the KSP values. We'll come back to an example of showing how this one works numerically in just a little while. Okay, now if you were to go back and look at the table of KSP values that we looked at, you might remember once again that the values themselves are very small. They're all less than 1, and some of them are on the order of 10 to the minus 20, 10 to the minus 30, 10 to the minus 40. It actually makes solving a lot of these problems a lot easier, because you can use sort of that mathematical assumption that x is going to be really small and sort of drop that out and solve them quicker instead of using the solver in your calculator. You can still use the solver in your calculator in solving these problems if you want to, but remember, when you are putting in that x value before you hit solve, you're going to have to put in a really, really small x value, because some of the answers are going to come back as really, really small. And if you don't put that in small enough, it may not give you a very good answer. So let's go ahead and look at some calculations. Let's calculate the solubility of silver chloride in water, given that its KSP is 1.6 times 10 to the minus 10. All right. Well, a lot of these, the first thing you're going to want to do is write the equilibrium that's going on. So silver chloride, we've got AgCl solid. So what ions does it break up into? It breaks up into Ag plus, aqueous, and Cl minus, aqueous. So you can sort of set up an ice type table for this if you'd like to. If you do set up an ice table for this problem, it's essentially, well, if it's in water, you've got no silver ion to start and no chloride ion to start. Your change is plus X, and so at equilibrium you've got X and X. So solving for your molar solubility, all you've got is KSP equal to the Ag plus concentration times the Cl minus concentration, or we've got 1.6 times 10 to the minus 10 equal to X times X, or X squared. So that makes that pretty simple to solve. You get X is the square root of 1.6 times 10 to the minus 10. So I'm going to go ahead and punch that in my calculator. 1.6 times 10 to the minus 10. And I end up with 1.3 times 10 to the minus, let's see, 1, 2, 3, 4, 5, minus 5 molar. So this X is the Ag plus concentration, the Cl minus concentration. This is also 1 to 1 with your silver chloride. So this is your molar solubility of the silver chloride. You could dissolve 1.3 times 10 to the minus 5 moles of silver chloride in 1 liter of water. And at that point it would be saturated. Let's try the same thing for the solubility of silver phosphate in water. So let's give ourselves a little bit of room up here to solve our problem. Once again, first step, write out our equilibrium expression. So we've got silver phosphate. That would be Ag 3PO4 solid in equilibrium with, that would be 3Ag plus and PO4 3 minus. All right, now here again, you could do the ice table if you want to, or if you want to sort of shortcut this, we could call this 3S and this S. S sort of just replacing X and calling it S for solubility. It's going to turn out, if you do the ice table anyway, 0 for the initials, plus 3 times for the silver, and then just 1 for the phosphate. So if we sort of shortcut this way, we can say KSP is equal to the concentration of Ag plus cubed times the concentration of the phosphate. Or if we plug in, we've got 1.8 times 10 to the minus 18 is equal to 3S cubed times S. Or if we simplify that a little bit, we have 1.8 times 10 to the minus 18 is equal to 3 cubed would be what? 3 times 3 is 9 times 3, so that's 27 S to the fourth. So solving for S, the solubility, we would have 1.8 times 10 to the minus 18 divided by 27, and then take the fourth root of that, and I get a number that looks something like 1.6 times 10 to the minus 1, 2, 3, 4, 5, minus 5 molar. That would be your molar solubility of silver phosphate. You could take 1.6 times 10 to the minus 4 moles, minus 5 moles of it, and dissolve that in a liter of solution before it is saturated. Okay, here is an example for us to try. This is a little bit backwards of what we were looking at. We've got the solubility of copper 1 bromide, CuBr, is 2.0 times 10 to the minus 4 molar. So therefore, what is the value of KSP? Once again, we can start by writing out our equilibrium expression. CuBr solid would break up to give a small amount of Cu plus and Br minus. So the solubility, well, it's 1 to 1 of that. So if we were writing S expressions of these, it would be S and S. So the KSP is equal to the Cu plus times the Br minus, which would be equal to S times S, or S squared. And well, we're given the molar solubility. We're given that it's 2.0 times 10 to the minus 4. These are all 1 to 1 to 1 with the CuBr. So we can simply plug in 2.0 times 10 to the minus 4 and square it, and we should get our KSP. So if I do that in my calculator here, let's see, 2.0 times 10 to the minus 4 and square that, I end up with 4.0 times, if I did this right, 10 to the minus 8, I believe, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So there you go. That's your KSP given the molar solubility. The next example here is very similar to the ones that I showed you just a little while ago. So why don't you pause the video here and see if you can give this one a try before you continue. Go ahead and pause and see what you come up with, and then unpause it, and I will show you what I get for an answer. Alright, so I've got our equation here, Ag2S breaks into 2Ag plus and S2 minus. So our KSP will be equal to Ag plus squared times S2 minus. I've already put here that we could call this S and this twice that 2S. So we can simply plug in our information here and solve. So we have 1.6 times 10 to the minus 49 equal 2s squared times s. In simplifying this a little bit, 2s squared is going to actually be the 2 squared, which is 4, times s squared times another s, so that's 4s cubed. This all still equal to 1.6 times 10 to the minus 49. So to solve for s, we're going to divide by 4 and take the cube root. So doing this, I'll get s, let's see, 1.6 times 10 to the minus 49 divided by 4 and take it to the cube root. And up with something that looks like 3.4 times 10 to the minus 17 molar. So that's a pretty low concentration, so it doesn't take very much at all before a silver sulfide solution is saturated. One more that's sort of like this. Again, why don't you go ahead and pause this and give it a try yourself first. See what you come up with. Alright, so if we plug in what we got here, we've got 1.1 times 10 to the minus 73 equal to 2s squared 3s cubed. So this side we're going to end up with 4s squared times 27s to the third. So let's see. that will ultimately be 108 s to the 5th equal to 1.1 times 10 to the minus 73. So solving for S, our molar solubility, we'll divide that by 108 and take it to the 5th root. 1.1 times 10 to the minus 73 divided by 108. And in my calculator, I'm just raising that to the 1/5 power. I end up with a value of 1.0 times 10 to the minus 15 molar. All right. Let's move on to our 4th example. Here we're looking at the molar solubility of iron 3 hydroxide. Well, here we actually have to take a small little extra thing into account. But let's start the normal way we would here by writing out our equilibrium. So what do we have? We've got FeOH3 solid in equilibrium with Fe3 plus and 3OH minus. All right, well, assuming this is in water, which most likely it is unless something is said otherwise, what's different about this versus any of the other things? Well, water has the pre-existing equilibrium of H plus and OH minus in the solution to start with. And if you remember from our good old KW, if it's pure water initially, you've got 1 times 10 to the minus 7 molar of H plus to start, and 1 times 10 to the minus 7 molar of the OH minus to start. Well, though that 10 to the minus 7 concentration with a KSP of 10 to the minus 38 may very well be significant here. So we're actually going to need sort of our ice table here. No Fe3 plus to start out, but we do have 1 times 10 to the minus 7 molar of the OH minus to start. So if we use S again for our solubility here, we could say plus S plus 3S. So at equilibrium, we've got S and 1 times 10 to the minus 7 plus 3S. So plugging into our KSP expression here then, we've got Fe3 plus times OH minus cubed, 4.0 times 10 to the minus 38 equal to S times, we'll just call this 10 to the minus 7 plus 3S cubed. All right, now here you can kind of have a choice to make as far as solving this in your calculator. One way is to just look at this and say, Well, this 3s compared to this 10 to the minus 38 is going to be a really small number. So we can eliminate this part of the expression here because s is going to be pretty small as to not really change the 10 to the minus 7 value here much. That's one way to go about it. That makes it a lot easier to solve. If you want to set this and put it in the solver in your calculator, just make sure that after you put the equation in, before you click solve, put that x as a really, really, really small number, 0.00000000000, lots of zeros, then 1, before you solve it. Otherwise, it may not get you what you're looking for. I'm just going to do it this way because it's simpler for me to solve. I'm going to get an s by taking 4.0 times 10 to the minus 38 divided by 10 to the minus 7 cubed. Once I do that, I end up with an s value of 4.0 times 10 to the minus 17 for the solubility of the iron 3 hydroxide. So if you have to do molar solubilities of hydroxides, you just have to remember, hey, I've got that existing hydroxide going on from the water equilibrium that I need to take into account. Okay, well, because hydroxide, OH minus, was part of that equilibrium, you can actually make iron 3 hydroxide more soluble in water if you lower the pH. If you make it more acidic, more H pluses, it will shift that right. Less OH minus, takes it some away. It's kind of a Le Chatelier's principle thing. So let's kind of redo this question, but what if we're looking for the molar solubility of the FeOH3, but now in a solution that's got a pH of 5? So the only real difference here is, well, instead of starting with an OH minus concentration of 10 to the minus 7, like in pure water, we can say, well, if you've got a pH of 5, well, 14 minus 5 is a pOH of 9. So we're dealing with a starting OH minus concentration of 10 to the minus 9. So instead of 10 to the minus 7's initial concentration, we'll have 10 to the minus 9. So plugging into the KSP, we'll have 4.0 times 10 to the minus 38 again, equal to the Fe3 plus, which is still going to be S, times 10 to the minus 9 plus 3S cubed. So now here we can once again simplify this by dropping that out, because this and this are so far different that S is going to be very small and not subtract or add much to that. So solving for S, we will get 4 times 10 to the minus 38 divided by 10 to the minus 9th cubed, we end up getting 4.0 times 10 to the minus 11 molar. You probably notice that is a larger number than what we had for just in pure water. In pure water, it was 4.0 times 10 to the minus 17 molar. So at a lower pH, more acidic pH, it was slightly more soluble. Shifted the equilibrium to the right because it removed some of the OH minus and allowed it to shift more in that direction. So looking at some of this stuff conceptually, you can look at this and say, how does any equilibrium change if you make it more acidic? So how would silver chloride solubility in water compare with that in an acidic solution? So just look at your solubility expression here again. Silver chloride gives Ag plus and Cl minus. And think about, is the H plus going to affect, if you add more H plus, that equal? Or in other words, could H plus combine with this anion, Cl minus? Is that going to combine with that to form HCl? Well, what do we know about HCl? HCl is a strong acid. Strong acids don't tend to want to go together to form like that. So no, that's not going to happen. So because of that, the addition of H plus isn't really affecting anything there. So the answer is they're going to be the same. So the bottom line question is, does the H plus from an acidic solution affect either of those ions? It doesn't. It's not going to combine with Cl minus to form a strong acid. So they end up being the same. How about silver phosphate? Well, let's look at this in a similar way. If we write the expression here, silver phosphate would be Ag3PO4 solid, giving 3Ag plus and PO4 3 minus. So how would H plus affect that? Well, would H plus combine with PO4 3 minus to form some HPO4 2 minus? Well, is HPO4 2 minus a strong acid? No. It would be considered a weak acid. So yes, that very likely would happen. In other words, PO4 3 minus is a pretty good base to be able to attract H plus and form this weak acid. So as you add H plus, it is decreasing the amount of the phosphate. Decreasing a product is going to shift the equilibrium more to the right according to Le Chatelier's principle. So it should be more acidic, or excuse me, more soluble in acidic solution. So the bottom line really is if your negative anion can combine with H plus to form a weak acid, it would do that. It would decrease the amount of that anion is there, shift the reaction to the right to compensate, making it more soluble. How does the KSP of silver phosphate in water compare to that of silver phosphate in an acidic solution? Well, the KSP is the same. The KSP is the KSP unless you change the temperature or you change the compound. So the solubilities may be different, but the KSP value itself does not change. It is still your equilibrium of silver phosphate breaking down into its ions. All right, going back to what we talked about a little while back, which of these two compounds has a higher molar solubility? Now, earlier on, when they were similar enough compounds, we were simply looking at their KSPs and saying, well, whichever one's got a higher KSP has a higher molar solubility. But these compounds are different enough that that may not be the case here. And so let's take a closer look at this. So if we look at FeCO3, it's going to break down to give Fe2 plus and CO3 2 minus. That's 1 iron to 1 carbonate. So when we do the KSP of Fe2 plus times CO3 2 minus, we essentially have 2.1 times 10 to the minus 11 equals S times S, or S squared. So we get the molar solubility by just taking the square root. Do that in my calculator. Square root of 2.1 times 10 to the minus 11, and I get 4.6 times 10 to the minus 6th, I believe, if I did this right. All right, so now let's look at the silver carbonate in comparison. We've got Ag2CO3 solid giving 2 Ag plus and a carbonate. So when we're solving this, we've got 2 of these to 1 of these. That is the big difference here. 1-to-1 ratio, 2-to-1 ratio. That might affect things a little bit. So let's look at our KSP. We'll have KSP equal to Ag plus squared times CO3 2 minus, or 8.1 times 10 to the negative 12 equals 2s squared times s, which is essentially, if you simplify that, 4s cubed. So solving for s here, I'm going to put in my calculator 8.1 times 10 to the minus 12 divided by 4, and then take the cube root of that, or raise that to the 1/3 power. So I end up with a solubility of this of 1.3 times 10 to the minus 4 molar. So which one's more soluble? This is a larger value, so the silver carbonate is more soluble, has a higher molar solubility than the FeCO3, even though its KSP is slightly lower than that of the FeCO3. The ratios of the ions make a difference here. All right, here's another good example to look at here as to how other pre-existing ions might affect a solubility. So calculate the solubility of AgCl in either a solution of calcium chloride or in a solution of calcium nitrate. So let's look at our equilibrium to see what we're dealing with here. So we've got AgCl solid in equilibrium with Ag plus and Cl minus. So the question really is, calcium chloride for part A here is Ca2 plus and Cl minus. Is the amount of those going to affect this equilibrium at all? Well, calcium really isn't going to do anything because calcium chloride is still soluble, so that's not going to affect anything. But chloride is an existing ion in here, so it's going to essentially give us an initial concentration of chloride here. So we can set up an ice table here for AgCl for part A. The volume doesn't matter, we're just dealing with the concentration here, so we can just look at 4.00 times 10 to the minus third. Now remember that calcium chloride is CaCl2, so if this is the concentration of calcium chloride, the concentration of the chloride there, since there's two of them, is going to be twice that. So our initial here can be 0 silver ion initially, but we're going to have 8.00 times 10 to the minus 3 molar of the chloride to start, plus S, so S and 8.00 times 10 to the minus 3 plus S. So when we solve that, we can say 1.6 times 10 to the minus 10 equals S times 8.00 times 10 to the minus 3 plus S. Once again, these numbers are far enough apart that we can assume that S is going to be a small number here and will not add much to that, so we can simplify that by crossing that out. Or you can do it in your solver again. Just make sure you put in a small enough x before you hit your solve. Either way, here I'm going to say 1.6 times 10 to the minus 10 in my calculator, divided by 8.00 times 10 to the minus 3. And I end up with an S that is 2.0 times 10 to the minus, let's see, 1, 2, 3, 4, 5, 6, 7, 8, minus 8 molar. Okay, now let's look at the calcium nitrate. Here we've got Ca2+, which we already said isn't going to necessarily affect anything, NO3-. Well, let's see. How might NO3- affect anything there? Well, is NO3- going to combine with silver to form like a precipitate or something? No, because silver nitrate is still soluble. So it doesn't really look like the nitrate's going to do anything either. So that means in the calcium nitrate solution, it's pretty much the same as if it were just in water. So we can change out this for the second problem to be 0 and plus S and S. So solving this is just like solving this in water. We've got 1.6 times 10 to the minus 10 equal S times S, or S squared. So solving for S is just the square root of 1.6 times 10 to the minus 10, which I get is 1.3 times 10 to the minus 5th molar. As you see in the calcium nitrate, or if it was just in pure water, it's more soluble than it would be in the calcium chloride. And that's because of a common ion, the chloride. You have an increase in that, it's going to shift the equilibrium that way, making it less soluble by having an existing amount of that ion in solution. All right. The last thing we're going to look at here is precipitation. If you mix two solutions of ions, will you get a precipitate? And this kind of goes back to comparing Q and K. So if Q ends up being larger than K, you end up having more ions in solution than the solution can hold, and so you will get a precipitation. If Q turns out to be less than or equal to K, you will have no precipitation because it'll either be unsaturated, it could have more ions in solution, or if it's exactly equal, saturated, still no precipitation. So Q is QSP, same expression as KSP, but you just plug in the concentrations of the ions that you've got, compare them to the K, and then you can see what happens. So let's look at an example. Will a precipitate form if we take 50 milliliters of 0.00025 molar sodium phosphate and mix it with 50 milliliters of 0.0025 molar barium chloride? All right, so first things first. If you're mixing these two solutions, what is the potential precipitate that could form? We could start out by saying, well, okay, if we have Na3PO4 combining with BaCl2, what we could possibly get here is NaCl and Ba3PO4 2. Now, we could balance that, but it doesn't really matter. We're just looking at this and this. Well, you probably remember from previous things that NaCl is soluble, so that's not going to be a possible precipitate. So we're really looking at Ba3PO4 2. That is our potential precipitate. Now, if I go back into that KSP table and look up the barium phosphate, we end up with a KSP for barium phosphate of 6 times 10 to the minus 39. Okay, So now we just need to look at the solubility equilibrium for that barium phosphate. So we can say Ba3 PO4 2 solid equilibrium with 3 Ba2 plus and 2 PO4 3 minus. But what are our concentrations of those that we're dealing with? Well, we've got these two solutions that we're mixing together. So by mixing them together, we're going to get new volumes to deal with. So we're going to have to do some M1V1 equals M2V2s to get the correct concentrations here. So I'm going to start by saying for the phosphate, we had 50 milliliters of 0.00025 molar phosphate equals, well, the new combined volume is 100 milliliters times M2. So the M2 for the phosphate is going to be, let's see, 0.00025. It's going to be 1.3 times 10 to the minus 4th for the phosphate. And I'll do likewise for the barium in the BaCl2. So we can say 50.0 milliliters of 0.0025 molar equals 100 milliliters at the end times M2. And so M2 for the barium ion is 1.3 times 10 to the minus 3rd. So now we can plug into our QSP expression those ion concentrations that we have, and we've got 1.3 times 10 to the minus 3 molar for the barium, and because of the 3 that's cubed, times 1.3 times 10 to the minus 4th molar for the phosphate, and because of the 2 that's squared, so we can get our QSP by multiplying those numbers. And when I plug that in, I end up with something close to 3.7 times 10 to the minus 17. How does that compare to the KSP? Well, that is much, much less than the KSP of 6 times 10 to the, that's actually much greater than 6 times 10 to the minus 39 of our KSP. This is a much larger number than that. So because of that, you can really say, well, that's way too many ions in solution for the solution to hold. So it is going to precipitate out. Yes, a precipitate will form because the QSP is greater than the KSP, so you will get a precipitate. All right, I hope this video helped you out with this topic. I will come back and post another video with some example problems of KSP from old AP exam.